At first glance, flatfish seem simple, quiet, passive. Halibut, turbot, sole, species with ancient silhouettes, gliding close to the seafloor, harvested in silence and packed into cold steel containers. Yet every year, over 4 million tons of them move across oceans to reach global markets. Beneath this steady migration is a complex and often invisible feat of logistics, one that rivals the intensity of mineral extraction, both in scale and precision. This isn't just about transporting food, it's about managing biological mass under thermal, mechanical, and metabolic stress. A challenge so delicate, so exacting, that it turns freight into a kind of underwater engineering ritual. Most people will never see the mechanical choreography behind this, but those containers, stacked on ships, humming below deck, chilled to tenths of a degree, carry more than fish. They carry the consequences of friction, torque, vibration, and every unseen variable that affects quality over days at sea. And here lies the problem. Fish flesh, unlike grain or frozen meat, is alive with residual cellular activity even after harvest. It responds to stimuli. It bruises under pressure. It suffocates in poorly ventilated environments, which means every ship carrying flatfish becomes a floating experiment in controlled decay, a moving boundary between freshness and waste. To solve this, logistics has borrowed from places few would expect. From naval engineering, where vibration-dampening protocols are developed for undersea cables that must survive continental drift. From precision agriculture, where sowing machines use millimeter-calibrated pressure to insert seeds without compacting the soil. These analogies aren't poetic, they're real engineering influences. Because the same principle used to protect fiber optic cables, distributing load evenly, minimizing shock waves, is now being applied to flatfish containers, where each pulse of turbulence in the ocean must be absorbed before it becomes damaged. And just as seed drills must place corn with surgical consistency, the way we load flatfish into refrigerated tanks matters. Uneven stacking doesn't just waste space. It elevates stress, triggers biochemical reactions, and weakens tissue structure long before the fish reaches a cutting board. But there's a crack in the system, one so small it often escapes inspection. When assembling refrigerated containers, a misapplied torque, just a few degrees off, can cause microfractures in the chilled water conduits that regulate internal temperature. These fractures don't cause immediate failure. Instead, they leak heat slowly, inconsistently, invisibly. And as temperature fluctuations ripple through the chamber, they distort the internal atmosphere like a cracked lens. Distorts light, enough to affect freshness, enough to undermine an entire shipment without anyone noticing until it's too late. So here's the question. If in mining, engineers use dynamic flotation beds to move raw ore without abrasion, why aren't we using similar kinetic principles to move live biomass more safely at sea? Why is a mineral treated with more thermal respect than a living creature with a metabolic memory? The answer lies not in a lack of technology, but in an outdated perception of fish logistics. A system that still treats cold storage as a matter of freezing and waiting, rather than managing life in suspended animation. This is not just this is biological engineering in motion. And it's time to look beneath the surface. Inside the sealed hull of a container vessel, where temperature is managed with surgical precision, lies a paradox that has plagued cold chain logistics for decades. Machines designed to preserve are often the same machines that quietly degrade. In the case of flatfish, this paradox emerges most vividly in the defrost cycles of refrigerated units. Uncalibrated defrosting, intended to prevent ice buildup, can send brief thermal shocks through the storage environment. These aren't dramatic spikes. Often they're barely perceptible on a standard display. But for halibut and turbot, whose muscle tissue continues subtle biochemical activity after harvest, even a minor disruption is a catalyst for stress. The fish reacts not with sound or motion, but through changes at the cellular. Glycolysis accelerates. Anaerobic pathways activate. The result is a loss of integrity in the flesh, invisible until it becomes spoiled. Traditional systems are blind to this. They read temperature, they regulate but they do not sense metal. This is where enthalpy sensors enter. Unlike simple thermometers, these devices interpret the energy content of the air, a reading that reflects both environmental and biological heat exchange. When installed inside cold chain containers, they offer something radical: the ability to adjust internal conditions based on the metabolic output of the cargo itself. In effect, the container listens to the fish, and when that metabolic signal rises, a warning of rising stress, the system responds not by overcooling, but by recalibrating airflow, adjusting defrost timing, and reducing internal. The implications are not theoretical. Studies show that a temperature drop from 1.2 degrees to 1.6 degrees over a 4-hour window increases spoilage rates by over 22%. The fish, deprived of stable thermal conditions, switches into a state of anaerobic stress. It consumes its last reserves of oxygen, altering pH levels and softening the. In a market that sells quality by the millimeter, this softness becomes written. Spoilage isn't rot, it's deation, a flesh that bends instead of slicing, a flavor that dulls, barely, but enough for the buyer to say. Some companies have begun to adapt. In Norway, a major exporter implemented thermal inertia modeling paired with onboard IoT sensors. These systems track not just air temperature, but the rate of change, identifying zones within each container where thermal stability breaks down. With this data, they mapped not just the cold, but the cold's consistency. And the result was astonishing: a $540,000 annual reduction in losses, achieved not by adding refrigerant, but by improving thermal prediction. But the most powerful insight may be the simplest. Rather than treat the container as a single unit, engineers began to analyze it by surface respiration rate, measuring how much oxygen the fish consumed per square. This reframing changed things. External temperature became secondary. What mattered was internal metabolic demand. The container was no longer a fridge. It became a living system, a controlled environment where every action had to respond not just to numbers, but to physiology. In marine logistics, success often hides in seas. It is not the loud failures that matter, but the quiet erosions, of texture, of temperature, time. Understanding thermal stress is not just about preventing loss. It's about respecting the silent biology that continues long after the fish see. If logistics fascinates you, check the pint. On the ocean, precision doesn't always fail because of genes. Often, it falters in the space between data and human. In the global transport of flatfish, where margins are measured in fractions of degrees and minute exposure, this disconnect can silently reshape an entire shipment's destiny. One of the most overlooked disruptions comes not from equipment malfunction, but from manual overrides during portions. Regulatory authorities, customs officials, or security teams, each with legitimate concerns, may interrupt automated ventilation cycles to perform their checks. What follows is often a cascade of unintended consequences: a delay of 20 minutes, a container left open too long, a defrost cycle. These may seem like logistical footnotes, but in the controlled environment of live biomass logistics, they become triggers, accelerating spoilage while leaving no trace. This is not a failure of protocol. It is a failure of system design, of not preparing the human interface to work with the intelligence already embedded in machines. To address this, logistics innovators have turned to an unexpected source: livestock transport analytics. These systems, originally developed to model animal behavior under movement stress, now inform neuromechanical simulations of human making. By predicting how personnel might override or ignore automated protocols under time pressure, these models allow for preemptive design, adjusting processes before errors occur. The result is a new kind of cold chain intelligence, one that plans not only for biology and machinery, but also for the fallibility of behavior. The impact of this is measurable. In a recent study across multiple freight routes, containers, equipped with real-time decision dashboards, visual displays that integrate biological data, container history, and AI alerts, experienced 34% fewer thermal anomalies than those relying solely on operator discretion. These dashboards do not eliminate control. They enhance it, translating complex variables into actionable visuals that reduce stress-inducing. The operators are guidelined. Their clarity. Some companies are further. A shipping route between Chile and East Asia faced an unexpected atmospheric disturbance. Ordinarily, this would have passed unnoticed till port arrival, but an onboard predictive spoilage algorithm trained on metabolic thresholds and external climate data flagged the deviation. Based on this alert, the vessel was rerouted, bypassing its original port to reach a closer cold chain terminal. The adjustment took 12 hours. It saved 18 tons of turbot from early decomposition. What makes this example notable isn't the software, it's the willingness to trust the data, to allow machine logic, when properly contextualized, to steer human decisions. In aviation, maintenance teams are trained using error propagation maps, diagrams that visualize how one decision can ripple through an entire system. When applied to marine cold chain logistics, these maps help operators see the fragility they manage daily. A single override isn't just a pause, it's a potential chain reaction. In the future of agricultural logistics, the interface between human and machine will not be about control. It will be about coordination, creating systems where sensor precision and human responsibility are no longer in competition, but in concert. Flatfish freight doesn't fail because we lack tools. It fails when we fail to listen to them. Precision has never been exclusive to the field. In agriculture, the logic of machines has long adapted to the variability of life. From sprayers that adjust flow rate leaf by leaf, to harvesters that modulate blade speed based on crop density. But now, this same agro-mechanical intelligence is crossing into ocean freight. The principles that guide irrigation nozzles in a soybean field are beginning to inform how cold diffusion modules distribute temperature inside a fish container. The result is not a transfer of technology, but a translation of logic, adapting the sensitivities of land-based systems to the moving, breathing cargo of marine transport. Onboard refrigerated fleets, this logic is becoming structural. The Maersk Reefer Division, for example, employs microclimate AI that constantly reassigns energy loads between different container zones, not based on temperature averages, but on the predicted metabolic output of the cargo inside. In practice, this means containers are no longer cooled uniformly. They are treated as ecosystems. Areas with higher biological activity receive more refrigeration power. Areas with stabilized cargo receive less. This reduces energy waste. Yes, but more importantly, it maintains physiological balance, preserving the biochemical integrity of the fish in ways no manual system could match. This shift demands a new mindset. Each container is no longer a static unit. It becomes a mobile, physiological chamber, a space where respiration, thermal exchange, and tissue resilience are continuously monitored and adjusted. Cold storage becomes dynamic, and with it, the responsibility of logistics shifts from simply preserving to actively managing a living chain of quality. The contrast becomes clear when we look at how different sectors evolve. In precision agriculture, irrigation systems adapt, flow per square meter. In some vineyards, they adapt per vine. In high-end greenhouses, they adapt per leaf. Yet in marine logistics, many systems still apply uniform protocols to tens of thousands of fish, as if all biomass were identical. But a flatfish at the edge of a container, exposed to more vibration, requires a different condition than one nestled at the center. Just like a sun-facing leaf needs less water than one in the shade. This insight leads to a final challenge, not one of equipment, but of vision. To treat refrigerated containers as active systems, not passive storage. To replace fixed thresholds with adaptive telemetry, just as precision farming replaced field-wide assumptions with real-time data per square foot. The tools exist. The models are proven. What remains is the integration, the willingness to bridge machines with biology in a way that respects. Because moving 4 million tons of flatfish across oceans is not just a question of logistics. It is a question of engineering empathy. A question of how far we're willing to go to preserve not just food, but the intelligence behind how that food moves. The cold chain is no longer cold. It is alive. And the more we understand it, the more invisible it becomes, until all that's left is the result. Freshness that feels effortless, but is in fact the consequence of machines thinking like farmers, and containers breathing like ecosystems. And speaking of what often goes unnoticed, take a second to check the pinned comment below. You might find something unexpected waiting for you there.